Okay, this is the topic of benzene that's in organic chemistry. Some of this you will have seen before, and some of it will likely be new. So the first part about benzene that you need to know about is the various bits of evidence that are available that its structure is actually the delocalized electrons. So that its most accurately represented structure is the hexagon with the circle around it. Okay, so there's some physical evidence, physical properties that support this, and there's also going to be chemical properties that support this. So the physical properties that support this are things like bond length. So the bond lengths are all equal, right? So if it was the alternating double single bonds, then you would have uneven bond lengths. You'd have 3 long bonds and 3 short double bonds, rapidly flipping back and forth between each other. But there's no evidence that that is taking place when they look at benzene, when they use scanning tunnel microscopes, or when they use X-ray crystallography to look at its structure and its bond lengths and bond angles. All of the bond lengths are equal, and they're all between a single and double carbon to carbon bond length. Okay. So a lot of evidence that they are sort of somewhere in between, but not a double or a single. The bond enthalpies are also in between a single and double C to C bond strength. Again, showing that they are somewhere in between, and there's not 2 different bond enthalpies. All bond enthalpies are equal. And the strength is actually closer to the double bond than it is to the single bond. So there appears to be some added stability that comes from the delocalization of electrons. The more you spread out charge, the more stable it gets. And so this is a more stable structure than if it were these alternating double and single bonds. And the last bit is are the isomers of benzene. When you have a 1,2 benzene structure, like 1,2 dichlorobenzene, there aren't 2 different 1,2 dichlorobenzenes. And if you had this structure at the top, if you had the alternating double and single bonds, there would actually be 2 different possible isomers, because you'd have a carbon here, and a carbon here, and a carbon here. And so it would be possible to have chlorine sticking off 1, 2 this way, or it would be possible to have them sticking 1, 2 that way. And those would be a little bit different because of the double and the single bonds. However, what we observe is that when you have 1,2 isomers, or when you have 1,2 structures on benzene, there aren't 2 different structures. There really is only one form, because it's actually even. So whether or not the carbons are sticking off of this one and this one, or this one and that one, doesn't matter. These 2 are 1, 2 are even to these 2. So the physical properties related to isomers is just that there is only one 1,2 isomer. All adjacent carbon atoms are equal. Okay, so they're not different depending on the double versus single bond. That delocalized ring means that any combination of a 1,2 is going to be the same as any other combination of a 1,2. Okay? That's the physical properties. And then there's a number of chemical properties. So one of the chemical properties has to do with the enthalpy changes associated with doing the hydrogenation reaction. So if you'll recall, the last topic was addition reactions, and the one where we added hydrogen was called hydrogenation or hydrogenation. And below it shows experimental values and theoretical values. So right here, you've got cyclohexene. Cyclohexene is a ring with 6 carbon atoms, and there's 1 C to C double bond. And when you add hydrogen to that, 1 hydrogen molecule to turn it into cyclohexane, down here, the delta H is about negative 120 kilojoules per mole. Okay? Now, if you have cyclohexadiene, So this one has 2 C to C double bonds. So you have to add 2 hydrogen molecules to it. It would have an IHD value of 2. 2 hydrogen molecules can fully hydrogenate it and turn it into cyclohexane. So everything down here is cyclohexane. Well, the change is almost exactly double what it is to hydrogenate the single carbon-to-carbon bond. So the theoretical value is that it should be exactly double. Turns out the change is not so much, but it's very, very close, just 8 kilojoules per mole different. So again, we add 1 hydrogen here, and it turns into cyclohexane. We get we get 120 kilojoules per mole released. If we do that twice, we get almost 240 released. It's about as close as we can get to. Let me add a 2 in there. As we can to getting exactly double. So then theoretically, if it was cyclohexatriene, so if there were actually 3 double bonds and we added 3 of these little hydrogens to it, then we would expect that the change should be somewhere on the order of negative 360, perhaps a little bit less, but pretty close, because you'd be breaking and forming 3 times the bonds that you are with the cyclohexene, the original. But in fact, when they are able to add 3 hydrogens to benzene, what they see instead is that the change is way, way smaller than that. So it implies that there is a real stability, that the actual benzene has a much lower starting potential energy, because the change to get down to cyclohexane is significantly less, almost half as much as they would predict. And so that implies that that ring is lowering the potential energy of benzene. So do it in a different color. Yep. And so what are we saying here? We're saying that the delocalized electrons lower benzene's potential energy. They give it stability. And perhaps it would be easier to read if I didn't put it right there. So I'm going to move it. Okay, but this is called a chemical property because it has to do with an energy change that's associated with a chemical reaction. And so that's why we're going to call this one a chemical property, that its enthalpy of hydrogenation is much less than if it had 3 carbon-to-carbon double bonds, almost half. So further evidence that it doesn't have 3 carbon-to-carbon double bonds. It has that delocalized ring. The last bit of chemical evidence you need to be aware of is that benzene does not readily undergo addition reactions. Right here is the standard addition reaction where you have carbon-to-carbon double bond, and it reacts with something, and the thing adds on to each carbon of the double bond. But benzene, it's very, very difficult to make benzene do this reaction, and it's much more common for benzene to undergo substitution reactions instead. So, for example, if we added chlorine to benzene, the addition reaction we would predict is that both the chlorines would add, and we'd get C6H6Cl2. But instead what we see is if we add chlorine, we end up getting C6H5Cl plus HCl. And so we end up getting a substitution reaction. So final bit of evidence is that benzene doesn't undergo sort of classic reaction of alkenes. It undergoes a substitution reaction. And the reasoning for that is that if you were to add something to benzene, it breaks up its ring. It breaks up that really stable delocalized electron ring. And so for benzene, it's much more preferable and more stable if it can just replace one hydrogen with one other species, whether it be a chlorine or something else, because that can keep its ring intact. So the 2 reactions that you need to be aware of, and this is at the SL level, they're both called electrophilic substitution reactions of benzene. They're called electrophilic because the thing that ends up substituting onto the benzene is an electrophile. Benzene, by its nature, by having this ring of electrons here, is very electron rich, and so it sort of acts as a nucleophile. It acts as something that is attracted to positive, and it's attracted to things that are electrophiles, things that like electrons. So The two overall reactions that you need to know, just simply without knowing the mechanism, is benzene plus nitric acid makes C6H5NO2, which is called nitrobenzene, and plus water. That's the overall balanced equation. The special conditions that you need are concentrated sulfuric acid, and it needs to be heated to at least 50 degrees Celsius. So again, this is just SL. You don't need to know the mechanism in SL. You just need to know that benzene can be converted to nitrobenzene using this combination of reactants and conditions. Okay? You should also be aware that benzene can be turned into chlorobenzene, with hydrochloric acid being the other product. And really, it can be turned into bromobenzene or iodobenzene in the same way. But the conditions are this aluminum chloride and dry ether as a solvent. Again, it's a little bit, just straight up memorization of what are the conditions and what are the reactants needed to add chlorine on or substitute a chlorine on for a hydrogen. So these are the SL reactions. There's not much more to it than that. Those are the details. So I'll stop the video here. So far, everything we've covered is standard level, knowing the evidence that is both physical and the evidence that is chemical for why it seems that benzene does not have alternating double bonds, but in fact has a ring of the delocalized electrons around itself.